Okay. So the first thing is this problem. If you can't remember the Turan's theorem, let me remind you, okay? Turan's theorem. So it's basically along the lines of if a graph doesn't have any triangles, how many edges can it have? Okay. So so like if a graph hasn't got any triangles, so no K3s, yeah, then the number of edges is at most like something like along the lines of floor of n squared on 4 or something.
All right. Yeah.
Or something like this, you know. But in general, Turan's theorem is like if it has no km plus 1, yeah, then the number of edges is at most the number of edges in the Turan graph, which is I prepared earlier is this number of edges. Okay. So in particular, if m equals 3, right? If m equals 3, yeah, then it's saying it has no k4s, right? That makes sense? No k4s. And if it has no k4s, then it can have at most this many edges. So n is eight. So in our case, let's say there's 8 vertices, yeah? Okay. Then this k becomes 2, yeah?
Yeah.
Okay, and then you have k plus 1 choose 2 is 3, yeah? M minus 1 is 2, yeah? And then n minus k is 6, 6 choose 2 is 15, yeah? So it's saying it can have at most 21 edges. Does that make sense? Okay. So how does our problem relate to this? Well, so we'll call this EMN. So the problem relates to this because we have 8 batteries, right? So that's 8 vertices, yeah?
Yeah.
And we can assume that if it's a complete graph. So you remember what the edges represent, right? The edges represent
if you pick those two vertices as batteries.
Yeah, so you could do that or the complement, okay? So the complete graph on 8 vertices has 28 edges, right? Yeah. 8 choose 2. So what you can do is you can pretend you start with a complete graph, and every time you pick 2 batteries to try, you remove the edge. Okay? So you remove edges between pairs tried, yeah? That makes sense? Okay, and now what your goal is, so your strategy is to try a certain number of batteries, right? So you remove a certain number of edges, right? And the thing is like, um, what does it mean for your strategy to succeed or fail? Well, it means that, so once you remove the edges, right, you can't find four vertices for which all the edges are there. So you can't find any K4s, right? Because anytime you have a K4, those could have been the good batteries, and you never tried them. So the problem becomes, um, yeah. So now you've made attempts to be removing edges. Now it becomes what's the most number of edges you can have without any K4s. Yeah, and then we know the answer is 21, right?
Oh, from Turan.
From Turan's theorem. So if you put it back into the problem, it means you need at least 7 attempts because 21 is 7 edges removed from 28. You know? Does that make sense?
Yeah.
Okay, so that sounds very fancy, and if you knew that in the exam, it'd be like a free ride. But, there's still ways of actually proving this. One cool way I thought Yeah. So if you quote the theorem, I think you're just done. But like you could obviously still prove it in this case. So I did something like this. So basically, what you do is you circle. So you take 8 vertices, right? And you basically just abuse the condition that every 4 you choose has to have an edge. Yeah. So I'm back to edges representing attempts. So if you do that, then you can kind of log with 3 edges. It looks like that, right? Because you can just choose these 4, and then something has to be connected. So up to symmetry is those 2, right? And you can choose like these 4, and then something has to be connected. So you can log basically 3 edges looks like that, you know. And then I picked these middle 4 vertices, right? And there has to be an edge, right? And so it either connects the isolated one to one of the other ones, or the other ones to each other. Yeah. So that gives you the 2 cases of the 4 edges. See what I mean? So assuming that's what you get for 3 edges, yeah.
Yeah.
Then picking 4 vertices that don't have an edge gives you the 2 cases for 4 edges. So either those 2 connect at the top, yeah, which gives you that one, yeah. What?
Oh,
Yeah, the top one,
I
yeah.
see.
Or the isolated one connects to the one of the edges, it gives you the second one, yeah.
Mm-hmm.
And you can do the same thing here. So if you pick these 4 edges that have nothing connected, it gives you 2 cases or 3 cases. So you can either connect it to each other or one of them to the ends here, right? And the same thing happens here. And then actually one of the cases repeats between these 2, so you only have 5. And then you do the same for 6 edges, and and then in the end you end up with 11 cases for 6 edges, yeah.
Mm-hmm.
And the fact that you can pick 4 vertices that have no connections means that all of them fail, you know. So that proves that you have to do it in at least 7, you know. And then of course there's the construction to do it in 7, which is the TED talk or the easy part of it.
Mm.
Which I guess, you know, it might be a trap if you watch the TED talk and just do that. You just only get like 2 or 3 marks. Okay, so that was quick. Any questions?
No.
That's kind of crazy. Turan's theorem came up twice in 1 week. Because like Lucas also mentioned that he solved one of the TST questions using Turan's theorem, ideas.
Mm.
And a lot of people didn't get it.